In this video tutorial, we will look at the topics of combined gas law, Dalton's law of partial pressures, and the ideal gas law. In our previous lesson, we discussed the three gas laws, Boyle's law, Charles' law, and Gay-Lussac's law. We saw that volume and pressure had an inverse relationship, meaning as one increased, the other one would decrease, but this only occurred at a constant temperature. By plotting experimental data, we saw that there was a linear relationship between these two variables, allowing Boyle to come up with this equation, V1 P1 is equal to V2 P2. With Charles' law, we saw that volume and temperature were directly proportionate, so if one increased, the other one also increased, but this only occurred at constant pressure. Again, using experimental data, Charles came up with the equation V1 over T1 equals V2 over T2. Finally, Gay-Lussac's law showed that pressure and temperature were also directly proportionate, so if one went up, the other also went up, so long as volume remained constant. From this, Gay-Lussac determined that P1 over T1 equals P2 over T2. So these gas laws do a great job showing the relationship between temperature, pressure, and volume of a gas. But as you can see, there's a major flaw. These equations only work when one other variable remains constant. So what can we do if all three variables change at the same time? Well, let's take a look at these equations. You'll notice that volume and pressure are always in the numerator. Meanwhile, temperature is always in the denominator. Putting these gas laws together, we get something called the combined gas law, where V1 times P1 over T1 is equal to V2 times P2 over T2. Really, this is the only equation you need to memorize. If temperature remains constant, then it doesn't change. If it doesn't change, it doesn't really affect my calculations. If it doesn't affect my calculations, I can remove them. And once you remove temperature, there's your equation for Boyle's law, V1 P1, V2 P2. The same applies for the other two variables. If they remain constant and they don't change, you can remove them. So remove pressure, and you have Charles' law. Remove volume, and you're left with Gay-Lussac's law. So by removing the variable that remains constant, you now have all three equations in one. Moreover, you're no longer restricted to situations where one variable must remain constant. All three variables can change, and you can still use this equation. Now, while experimenting with gases during a chemical reaction, Gay-Lussac noticed something strange. When he combined 2 liters of hydrogen gas with 1 liter of oxygen gas, they reacted together to produce 2 liters of water vapor. Do you see what's strange? How about now? How can 2 liters of hydrogen gas react with 1 liter of oxygen gas, but only produce 2 liters of water vapor? So Gay-Lussac realized that during a chemical reaction, these volumes are not additive. But let's take a look at the balanced equation for this reaction. It would seem that the volume ratios in the chemical reaction are identical to the stoichiometric ratios in the chemical reaction. Now, as we know, mass ratios would not work. 2 grams plus 1 gram would not equal 2 grams. But the volume ratios did match up, even if the mass ratios did not. Based on this information, Gay-Lussac came up with the law of combining volumes, which states, so long as temperature and pressure remain constant, gases will react in whole number ratios based on volume. With this discovery, John Dalton also noticed that the masses of the elements that combine can also be expressed in small whole number ratios. However, these ratios and these ratios did not match up, which is where Avogadro comes in. He converts Dalton's mass ratios into mole ratios, and now discovers that the mole ratios and the volume ratios are identical. So with the mass ratios, you had to convert them to moles first before you could do your stoichiometry, then pop it back up from the land of the mole into a mass. But with volumes, you could just go directly into their ratios. There's no need for you to convert them to mole because these ratios are identical. So that's nice, saves you an extra step. Just don't forget to balance your equations because that's where we get our stoichiometric ratios from. Now Avogadro takes it a step further and notices that as long as the temperature and pressure remain the same, equal volumes of all ideal gases contain the same number of molecules. Meaning if I had 2 liters of hydrogen gas and 2 liters of nitrogen gas, so long as they are both at the same temperature and same pressure, they both have the same number of molecules. It doesn't matter what gas we're talking about, equal volumes of any ideal gas will contain the same number of molecules. Now this only works if these gases behave ideally, but as we saw in a previous lesson, most gases will behave ideally so long as the conditions remain standard. And for this course, we will be working under standard conditions such as STP and SATP. Now let's think about the situation for a second. If I place more chlorine molecules into my balloon, so I'm going to pump more chlorine in, what do you think will happen to the volume of this balloon? Obviously, it will increase. So if I increase the number of molecules inside my balloon, I increase the balloon volume. That is, so long as the temperature and pressure don't change. So based on this observation, moles and volume have a direct or indirect relationship. What do you think? Well, if increasing one increases the other, it must be a direct relationship. And that's where we get this equation, where N1 over V1 is equal to N2 over V2. N1 represents the mole of gas number 1, N2 represents the mole of gas number 2. Now, molar volume is defined as the volume that is occupied by 1 mole of a gas. So its units are measured in liters per mole. So it's kind of like the opposite of molar concentration, where molar concentration would have been moles per liter, molar volume is liters per mole. Now, another thing to keep in mind is that the molar volume of any ideal gas at STP is 22.4 liters per mole. So that's any gas, as long as it's behaving ideally. Doesn't matter if it's nitrogen, oxygen, fluorine, chlorine, whatever. 1 mole of any gas at STP has a volume of 22.4 liters. As a reminder, standard temperature and pressure is defined as 0 degrees Celsius, but we can't use Celsius. We have to always convert to kelvins. When you do so, it's 273.15 kelvins. And standard pressure is defined as 101.3 kilopascals. Alright, so let's try out this question. A balloon full of nitrogen gas has a volume of 1.30 liters and an internal pressure of 98 kilopascals at 22 degrees Celsius. So I'm going to fill in my information here, and don't forget to convert to kelvins. Now the total mass of the balloon and gas is 6.18 grams, while the balloon mass is 4.73 grams by itself. So if I subtract these two masses, I'm then left with the mass of the nitrogen gas, which is 1.45 grams. The question then asks, what is the molar volume of nitrogen gas at STP? So because they're giving me a new set of conditions, I need to have P2 now and T2 and label these ones as V1, P1, T1. So one situation, another situation. Now it's asked me to solve for molar volume, and if you recall, the units for molar volume are in liters per mole. Since liters is the units for volume and mole is the unit for mole, the equation is volume per mole. So now I need to calculate volume and mole. Since mole is equal to mass divided by molar mass, I've got the mass of the nitrogen gas, I've got the molar mass of nitrogen gas. Don't forget to multiply by 2 because nitrogen is diatomic, and you get 0.0517 moles of nitrogen gas that I can plug into this equation here. To solve for volume, I'm going to use the combined gas law because nothing here remains constant. In this case, we already have V1, so we're going to be solving for V2. Rearranging this equation to solve for V2, we get this. I can then substitute my values in, and I get 1.16 liters for volume 2. Substituting these values into the equation, we get 22.4 liters per mole as the molar volume of nitrogen gas at STP. Now, the sad thing is, this whole question, it's only worth 1 mark. That's because the molar volume of any gas at STP is always 22.4 liters per mole. In this case, we're discussing nitrogen gas at STP, 22.4 liters per mole. Doesn't matter what identity the gas is. As long as it's at STP and the gas is behaving ideally, we've got 22.4 liters per mole as the molar volume. So please remember this value. There will be some questions in the textbook where you won't be able to solve it unless you remember this factoid, that any gas, its molar volume at STP will be 22.4 liters per mole. Just like this question, if you didn't know what STP was, 101.3 and 273.15, you wouldn't have been able to solve this question. So anytime you see STP in a question, 22.4 liters per mole should be in the back of your head. You may not need it for every question involving STP, but it is still considered to be a given, even if it's not directly or explicitly given in the question. So we have these two equations now, combined gas law and Avogadro's law. What I'm going to do is I'm going to switch the numerator with the denominator for Avogadro's law, and now volume appears on the numerator for both equations. I can now combine these two equations to give me this relationship. But in its current form, it's not particularly useful. I mean, there's nothing else on this side of the equal sign. But if I solve for 1 mole of an ideal gas at STP, plugging in 101.3 kilopascals for pressure, volume, of course, for any ideal gas at STP is 22.4 liters, temperature is 273.15 kelvins, and 1 mole, I get this value, 8.314 kilopascal liters per mole Kelvin. This value is known as the universal gas constant. No matter what gas we use, the ratio of PV to Tn is always going to be 8.314. That's why it's called a constant, because it will not change, regardless of the identity of the ideal gas. So this is yet another number you have to memorize, as it will not be provided for you on tests or in questions. To help my students remember this, I use the following story. I ate some pie. Get it? 8 sounds like 8, and 314 reminds me of pie. So I ate some pie, and I drank some milk. What is milk? It's moldy milk. And surprise, surprise, kapow! I got diarrhea. Alright, so I ate some pie, I drank some milk with it, some moldy milk, and then kapow, diarrhea. Now it's important to note you must use kilopascals when measuring pressure, you must use liters when measuring volume, and you must use Kelvin when measuring temperature. If any of these units change, this value also changes as well. So rather than memorizing a brand new R value, a brand new universal gas constant, I'd rather just change and convert my units into kilopascals, liters, moles, and kelvins. Alright, so now that we have PV over NT is equal to R, I can rearrange this equation and I get PV equals nRT. This is known as the ideal gas law equation. So let's try it out. An unknown gas has a density of 7.476 grams per liter at 135 kilopascals and 12 degrees Celsius. So I'm going to organize this under my givens. Just remember to convert your Celsius into kelvins. It then asks what is the identity of this element. Typically, when you're trying to find the identity of a mystery element, you're probably looking for its molar mass, so you can look it up on the periodic table afterwards and identify which element it is. To solve for molar mass, we divide mass by mole. Now the problem is we have neither mass nor do we have mole. Neither of these variables is here. So the trick to this question is to assume a 1 liter sample. I can do this because it doesn't change anything. If I had 500 liters of this substance, it's still the same unknown gas, it still has the same density. If I had 2 milliliters of the substance, it's still the same unknown gas, it's still the same density. So you can choose whatever sample size you want. I chose 1 liter because the density is 7.476 grams per liter. Since density is equal to mass divided by volume, plugging in the density and my assumed volume, I now have a mass of 7.476 grams, which I can then plug in over here. So now all I have to do is solve for mole. For that, I use the ideal gas law. Rearranging it, I get N is equal to PV over RT, so remember N represents moles. I can now substitute the values in. Notice, however, for volume, I chose a 1 liter sample, I must plug that one in. So remember, you didn't have to choose a 1 liter sample. You can choose whatever you want. You can choose your student number. In the end, whatever volume sample you chose must be plugged into the equation as such. But do you see now why I chose 1 liter? It makes my calculations much easier. You'll notice also I didn't write down the universal gas constant because you should have that memorized. It's a given. And solving for this equation, I get 0.05694 moles of my mystery substance. I can then plug it into this equation, giving me 131.3 grams per mole as the molar mass of a mystery substance. Looking at the periodic table, we see that xenon has a molar mass of 131.29, so that's our mystery substance. Alright, what I want you to do is try this question out yourself. Press pause. When you're ready, press play, and we'll take it up together. Alright, so this is another mystery element situation. So that means I need to calculate molar mass. I'm going to organize all my information in here, but you'll notice that it just says SATP. So you have to know what standard ambient temperature and pressure are. In this case, 25 degrees Celsius, or 298.15 kelvins, and 100 kilopascals. So make sure you remember the values for STP and SATP. So the equation for molar mass is mass divided by mole. I have the mass up here, 14.873 grams, so I'll plug that in. All I have to do now is solve for mole. For that, we'll use the ideal gas law, rearrange it to solve for mole. N is equal to PV over RT. I'm going to start plugging my values in. Now, unlike the last question, for this one, you should not assume a 1 liter sample. The question actually gives you the volume here, 5.2 liters. You can't just change the question. So because they give me a volume, I can't just assume any volume I want. Alright, so plug in the 5.2. Again, 8.314 is the universal gas constant, not given to you. You should already know that one. And then your temperature, 298.15 kelvins. Solving for this, I get 0.20977 moles that I can plug into this equation. And that gives me 70.90 as the molar mass of my mystery substance. But it mentions that the substance is diatomic, meaning this is the molar mass of 2 of these atoms. As such, I'm going to divide by 2, giving me a molar mass of 35.45, and hopefully by now you recognize that molar mass as being chlorine. Let's move on to our next topic, Dalton's Law of partial pressures. According to John Dalton, the total pressure of a mixture of gases is the sum of the individual pressures, the partial pressures of each gas. Now, when I first read this law, I thought, really? They named a law after you for this? Essentially, what he's saying is the total pressure inside the balloon is equal to the pressure exerted by the oxygen plus the pressure exerted by the hydrogen plus the pressure exerted by the nitrogen. So the total pressure is equal to the pressure of the individual gases inside. Wow, my mind is blown. I mean, I hope this is pretty obvious, and he did have to experimentally prove this, but it's just so odd that there is a law named after something so obvious. But in any case, this is the easy part. But if you look at the law a little more carefully, we suddenly realize that if oxygen makes up 25% of the total volume, then it makes up 25% of the total pressure. I mean, that also makes sense, but again, he had to prove this experimentally. So with hydrogen, because it makes up 15% of the total volume, it also makes up 15% of the total pressure. And nitrogen, 60% of the total volume, 60% of the total pressure. Thus, the partial pressure of oxygen, so the pressure exerted just by the oxygen, is 25% of 200. And that comes out to about 50 kilopascals for oxygen, 30 kilopascals for hydrogen, and 120 kilopascals for nitrogen. And you'll notice if we add up the partial pressures of each gas, they add up to the total pressure. Now, Dalton's law of partial pressure seems pretty straightforward, but it can be applied to more interesting questions, like this one for instance. For me, if I find that a question is too wordy, I will try to draw a diagram to help me understand the question. So here I have an 8-liter balloon, so V total is 8 liters, and an unknown volume of hydrogen gas and an unknown volume of helium gas. If the partial pressure exerted by just the oxygen is 27 kilopascals, what is the total internal pressure of all the gases? So here I have the volume of the oxygen, I also have the total volume, and I have the partial pressure of just the oxygen by itself. I don't know how much hydrogen is inside, I don't know how much helium is inside, but I need to find what's the total pressure inside this balloon. So we're going to use Dalton's law of partial pressures to solve this question. Since I know that 2 liters of oxygen gas is the same as saying 27 kilopascals, then I can set up a ratio to determine how many kilopascals 8 liters would exert. So 2 liters represents 27, 8 liters representing x, solve for x, and we get the total pressure is 108 kilopascals. Now let's double check to make sure that works out. So I know that oxygen makes up 2 liters and the total is 8 liters, so 2 out of 8 is 25%. If you recall, since oxygen is 25% volume, it should be 25% by pressure as well. So let's double check. 27 kilopascals is the pressure of the oxygen. We calculate the total to be 108, so that comes out also to 25%. So not only is the oxygen 25% by volume, it is also 25% by pressure. So there are many different ways to solve this question. This is just the most direct route to get there. Some students find it helpful to solve it this way, where they first find out what is the percentage by volume of oxygen. So 2 liters out of 8 is 25%. Then they'll take this 25%, plug it in here, and know that whatever x value is supposed to be, 27 out of this x value should equal 25%. Then just solve for x. So solve it in whatever way makes sense to you. Now, when you're in the lab, it's a little difficult to measure the volume of a gas because most gases are clear and colorless. To help us see the gas, we tend to collect them over water via displacement. So what we do is we fill a graduated cylinder with water and place it inverted inside a bucket. As long as the opening of the graduated cylinder doesn't break the surface tension, the water stays inside. We then seal a chemical reaction inside a flask and allow the gas that's produced to bubble up and into the graduated cylinder. As the gas fills up the graduated cylinder, it pushes out the water, and now we can see how much gas is being collected because there's a phase boundary between the gas and liquid states. So we can see it in action over here. As the gas is being produced, it goes into this tube, coming up and bubbles up. We can see the gas now because normally it would just be clear and colorless, but because I can see the water line, I can also see the gas line as well. And then once the reaction's over and all the bubbling is done, you can measure the volume of the gas you collect. So this method is called gas collection over water or gas collection via displacement. Now there is a problem with this method in that the gas that you collect is now wet. As the gas travels through the water and into the grad cylinder, it pulls water molecules with it. Furthermore, there's also some evaporation that occurs between the water inside the grad cylinder and the gas phase. As such, the pressure that you measure here is not just the pressure of the gas you collect, but also the pressure of water vapor bouncing around as well. To compensate for this, we must subtract the pressure of the water from the total pressure of the gas inside the grad cylinder. In so doing, by removing this water pressure, we're left with just the pressure of the gas itself. From there, we can plug in this number into our calculations and we're good to go. But if you had plugged in the total pressure instead, you would have overestimated how much pressure was exerted by the gas, because it's not just the gas in there, there's also water pushing along, adding to the pressure and causing you to overestimate your final values. To determine how much pressure is exerted by the water, we consult our water vapor pressure tables. So depending on the temperature of the water, you can find out how many kilopascals of pressure is exerted by the water molecules. Most of us know that in the winter, the air is pretty dry. That's because at colder temperatures, there's not a lot of water vapor sitting in the air. Most of that water freezes and condenses out of the air rather than staying as a gas. So that's why the vapor pressure of water at low temperatures is very low. In hotter temperatures though, things can get a lot more humid. The higher the temperature, the more water evaporates, and thus, with more water vapor present, higher pressure exerted by the water vapor. Now another problem we might encounter is, how do you measure the pressure inside the grad cylinder? I mean, the space inside here is very, very small, so how do you actually put a device, a barometer, in there? The answer is you don't. Think about it this way. The air pressure outside of the collection device pushes on the water in the bucket. By pushing on the water, it forces the water up into the gas collection device. Meanwhile, the gas pressure inside the collection device pushes right back. And if this water line doesn't move, then that means these two pressures are equal. If they were unequal, let's say the atmospheric pressure was more powerful than the interior pressure, then this water line would be moving up. Or if the interior gas pressure was more powerful than the atmospheric pressure, then this water line would be moving down. But so long as that water line remains still, you know that the pressure outside, the atmospheric pressure, is equal to the total pressure inside the gas collection device. As such, there is no need for you to shove a barometer in there. Just measure the barometer outside and make sure this water level isn't moving, and you know that the pressure inside equals the pressure outside. In order to make our volume measurements consistent, we have to make sure that the water line inside the collection device is at the same level as the water line outside the collection device, so the water line of the bucket itself. So this water line over here should match up with this water line. So you raise or lower this device, the collection flask, until both water lines line up. Then we can properly measure the volume of the gas that was collected. Alright, so let's try this question out. This one pretty much includes everything we've learned in the entire course, so let's give it a try. 4.72 grams of aluminum reacts with 89 milliliters of 0.760 molar hydrochloric acid. If this reaction has an 83% yield, what volume of gas can be collected over water at SATP? So the first step is to write out the equation, and don't forget to balance it. So this is a single displacement reaction, aluminum reacting with hydrochloric acid. You're going to check your activity series. Aluminum is higher than hydrogen, so that's fine, so it's going to displace it. Hydrogen gas will pop out, so we want to know what volume of hydrogen gas will be produced in this reaction. Alright, so 4.72 grams, concentration and volume for the hydrochloric acid. Don't forget to convert your milliliters to liters, and we're going to find out what the volume of hydrogen gas being produced is. As always, if you have no clue what to do, convert to moles. With this side, we're going to use mole equals the mass over molar mass, punch that in, and we get 0.1749 moles of aluminum. But on this side, we're going to use mole is equal to C times V, C 0.760 molar, V 0.089, multiply them, and you get 0.01557 moles. I'm going to use my ratios now to figure out who's my limiting reagent. 6:3 ratio, so divide by 6, multiply by 3, and you get 0.007785. This is a 2:3 ratio, so divide by 2, multiply by 3, and you get 0.2623 moles. Based on this information, aluminum is my excess reagent, while hydrochloric acid is my limiting reagent. So I'm going to ignore this and continue on with this. To find the volume, I'm going to use the ideal gas law, P equals nRT. Rearranging it, we get V equals nRT over P. Because this reaction occurs at SATP, so standard ambient temperature pressure, I know that ambient temperature is 298.15 kelvins, while ambient pressure is 100 kilopascals. I'm going to punch in 8.314 as my universal gas constant and take my mole value and substitute in here. But there's a problem. If you read the question carefully, it says collected over water, which means I don't just have hydrogen gas inside, there's also water vapor inside as well. So this pressure of 100 kilopascals is false. It is an overestimate. This 100 kilopascals is not just my gas, there's water inside. I need to get rid of this water. For that, I need to consult my vapor pressure of water. Since this reaction is occurring at SATP, so 25 degrees Celsius or 298.15 kelvins, I see at 25 degrees Celsius, the pressure of water is 3.2 kilopascals. I can now take my total pressure, subtract the pressure of the water, and I'm left with just the pressure of my hydrogen gas. Having properly adjusted the pressure, I can now calculate it to be 0.199 liters of hydrogen gas being produced. But am I done? No! We also need to factor in the 83% yield. So 83% of 0.199 liters is 0.165 liters of hydrogen gas that will actually be produced. Alright, so there you have it. This question pretty much has everything. Just make sure you remember, anytime a question says collected over water, you have to consult your water vapor pressure table. Then subtract it from the total pressure in order to get the proper volume of gas being produced. Because without this, you'd be overestimating the volume of gas you actually have. Alright, let's do one last question. What is the density of air at SATP? You can assume that air is 80% nitrogen and 20% oxygen. So this question is a little different in that it's a mixture of gases. Furthermore, it doesn't really give you that much information. So what I'm going to do is I'm going to assume a 1 liter sample to start things off, because the density of the gas remains constant regardless of how big your sample size is. So I'm going to assume a 1.00 liter sample just because I want to make my calculations easier. But again, you don't have to choose 1.00 liters. You can choose whatever volume you want. Just make sure that whatever you choose up here, you must carry this value throughout your calculations. Since this occurs at SATP, ambient temperature 25 degrees Celsius or 298.15 kelvins, ambient pressure 100 kilopascals. Now it's asked me to calculate density. The equation for density is mass over volume. But it's not the density of just one gas, it's a density of two gases mixed together. As such, the density of air is equal to the mass of the nitrogen gas plus the mass of the oxygen gas divided by the volume. But again, I chose a 1 liter sample, so whatever I chose, I must place over here. So you'll notice why I chose 1 liter. It makes my calculations a lot easier. So what should I look for next? Well, I got to find the mass of nitrogen and the mass of oxygen. The equation for mass is equal to mole times molar mass. I know the molar mass of nitrogen. Don't forget it's diatomic, so it's 2 times the 14.01, give me 28.02. Same with the mass of oxygen. I know the molar mass of the oxygen, 32 grams per mole, because it's diatomic again. So what am I missing? I'm missing the mole values. So what I like about this method is I'm starting from the end, and I'm working my way back to the beginning. By starting at the end, it always tells me what I need to look for next. So density, that's what I'm trying to calculate, mass over volume. Alright, well I've got the volume, so that means I gotta find mass. Punch in mass equation. Mass equals mole times molar mass. Well, I've got the molar mass of each, but I don't have the moles, so I need to look for the moles as my next step. For that, I'm going to use PV equals RT, rearrange the equation so that N, moles, is equal to PV divided by RT. Now, I assumed a 1 liter sample for the volume, so I gotta keep that as 1 liter here and 1 liter here. Universal gas constants 8.314, 8.314. This occurs at SATP, so I know the temperature in both cases, and I know the pressure in both cases. But there's another problem. This mixture is 80% nitrogen. So how can 80% nitrogen exert 100% of the total pressure? It can't. But according to Dalton's law of partial pressure, if nitrogen is 80% of the volume, it should be 80% of the pressure. So 80% of the 100 kilopascals gives me 80 kilopascals, while 20% of 100 kilopascals gives me 20 kilopascals. Now, a common question I get asked is, should I apply the 80% to the volume as well? The answer is no. Yes, nitrogen takes up 80% of the volume, but it isn't restricted to 80% of the space inside the balloon. It's not like there's 20% of the balloon where the nitrogen gas cannot be allowed to travel. No, it can travel anywhere it wants in the entire volume of the balloon. So because it's allowed to travel anywhere it wants inside the balloon, it must exert this 80% pressure over the entire 1 liter volume of this container. Alright, so only factor in the 80% composition into the pressure part, but not into the volume, because this gas, even though it only makes up 80%, can travel anywhere it wants in the entire balloon. The same goes for oxygen. It makes up 20% of the composition, but it's allowed to travel anywhere it wants in this entire balloon, so we keep it as 1 liter. Punching these into the calculator, I get 0.03227 moles of nitrogen gas and 0.008068 moles of oxygen gas. I can then substitute these values into the top, giving me 0.904 grams of nitrogen and 0.2581 grams of oxygen. Plug these values into my density equation, and I get 1.16 grams per liter as the density of air at SATP.